The year is 1942. Somewhere over the English Channel, an American-built fighter aircraft is climbing toward a formation of German bombers. The pilot pushes the throttle forward, watching his altimeter needle creep past 20,000 feet. And then, something begins to go terribly wrong. The engine, an Allison V-1710, starts to gasp. Power bleeds away. By 25,000 feet, the aircraft that looked so promising on paper has become little more than a sitting target. This is the P-51 Mustang, and it has a fatal flaw hidden deep within its engineering DNA. The question is not whether this fighter will fail. It already has. The question is whether anyone can diagnose the problem before it's too late.
The chain of causation that would eventually lead to one of aviation's greatest engineering rescues began in early 1940 in the offices of the British Purchasing Commission in New York City. Sir Henry Self, the man responsible for Royal Air Force production, research, and development, had been given a nearly impossible task. Britain was running out of aircraft. The Battle of Britain had not yet begun, but the strategists in London could see the storm clouds gathering. They needed fighters, and they needed them fast. The British initially approached North American Aviation with a straightforward request. They wanted the company to manufacture the Curtiss P-40 Warhawk under license. It was a known quantity, a proven design, and Britain needed volume more than innovation. But James H. Kindleberger, the president of North American Aviation, a man known to his colleagues as Dutch, made a counter-proposal that would change the course of aviation history. He believed his company could design and build a superior fighter from scratch, and he could do it in 120 days. From January to April 1940, John Atwood of North American Aviation spent countless hours at the British Purchasing Commission's offices in New York. The discussions were technical, precise, and collaborative. British engineers, many of them veterans of the aerial campaigns already raging over Europe, provided detailed specifications based on hard-won combat experience. They knew what worked and what failed when metal met metal at 400 miles per hour. They knew the exact requirements for armament, armor placement, fuel capacity, and structural integrity. These were not theoretical preferences. They were lessons written in the blood of fallen pilots. Sir Henry Self insisted on one crucial condition before the project could proceed. North American Aviation had never designed a fighter aircraft. Their expertise lay in trainers and medium bombers. Self demanded that they obtain the complete drawings and wind tunnel test results for the P-40s from Curtiss before presenting any detailed design proposals. This was not an insult. This was engineering due diligence. You do not send men into combat in an unproven airframe without understanding every aerodynamic principle that might save or kill them. North American Aviation purchased the drawings and data from Curtiss for 56,000 British pounds. If you're finding this investigation into aviation history compelling, take a moment to subscribe to the channel and ring that notification bell. There's more crucial evidence to examine in the case of the P-51. The resulting design emerged from a fusion of American manufacturing capability and British operational wisdom. Edgar Schmood, a brilliant aeronautical engineer who had been born in Germany and trained across Europe, led the design team. Alongside him worked Raymond Rice and Edgar Labour. They incorporated revolutionary features: a laminar flow wing designed to reduce drag, a radiator system positioned beneath the fuselage that actually produced thrust, and a structure optimized for mass production. The British Purchasing Commission approved the final design drawings on the 4th of May, 1940,
and firmly ordered 320 aircraft on the 29th of May.
The first Mustang rolled off the production line and made its maiden flight on October 26, 1940. It was delivered to the Royal Air Force in April 1942. The aircraft performed beautifully at low altitudes. It was fast, maneuverable, and carried significant firepower. The British designated it the Mustang Mach 1, and it quickly proved its worth in ground attack and tactical reconnaissance missions. But there was a problem, a critical systemic problem that became increasingly apparent as operational data accumulated. The failure point was the engine. The Allison V-1710 was a superb power plant in many respects. It was reliable, relatively easy to manufacture, and produced excellent horsepower at low altitudes. But the Allison used a single-stage, single-speed supercharger. This is where the physics of failure becomes crucial to understanding. A supercharger compresses air before it enters the engine's cylinders, allowing the engine to produce more power. At sea level, where the atmosphere is dense, the Allison performed admirably. But as altitude increases, the atmosphere becomes thinner. There are fewer air molecules per cubic meter of space. The single-stage supercharger could not compensate adequately for this reduction in atmospheric density. The performance degradation was not subtle. It was catastrophic. At sea level, the P-51 could achieve speeds approaching 380 miles per hour. But by 25,000 feet, where German fighter interceptors operated with impunity, the Mustang was down to barely 1,000 horsepower. By 30,000 feet, the aircraft was essentially helpless. It could not catch bombers. It could not escape fighters. It could not fulfill its intended mission. This was not a design flaw in the traditional sense. The Mustang airframe was exceptional. The wing design was advanced. The cooling system was innovative. But the engine, the heart that was supposed to give this bird life at combat altitude, was fundamentally inadequate. It was as if someone had built a racing car with a lawnmower engine. All that aerodynamic potential was being strangled by a power plant that could not breathe in the thin air where modern air combat occurred. The British recognized the problem first. Their engineers had extensive experience with high-altitude combat. They understood the operational requirements in ways that American planners, who had not yet engaged in sustained aerial warfare, could not fully appreciate. And they had a solution. It was sitting in the engine bays of their Spitfires and Hurricanes, the Rolls-Royce Merlin. The Merlin was an engineering masterpiece. Its critical advantage lay in its two-stage, two-speed supercharger system. Where the Allison's single stage could only compress air once before it entered the cylinders, the Merlin compressed air twice. The first stage provided initial compression. The second stage compressed the already compressed air further. This sequential compression allowed the engine to maintain power output at altitudes where the Allison wheezed and struggled. But there was a thermodynamic challenge that Rolls-Royce had to solve. Compressing air generates heat, tremendous amounts of heat. The Merlin's two-stage supercharger could raise intake temperatures to as much as 205 degrees Celsius. At these temperatures, the fuel-air mixture would detonate prematurely, destroying the engine from within. To prevent this catastrophic outcome, the Merlin used an intricate intercooler system. Passages were cast directly into the supercharger housing. An additional cooling core was positioned between the supercharger outlet and the intake manifold. 36 gallons of ethylene glycol per minute flowed through this labyrinth, absorbing heat and allowing the engine to produce power
without self-destructing.
Rolls-Royce test pilot Ronald Harker flew a Mustang Mark I in April 1942. His assessment was immediate and unequivocal. The airframe was extraordinary. The engine was holding it back. He recommended that a Merlin be fitted to the Mustang as quickly as possible. At Rolls-Royce's facility at Hucknall, engineers began the work of mating British heart to American body. The British prototype flew in October 1942, approximately 1 month before an American team completed a similar conversion. Both teams reached the identical conclusion. The combination of the Mustang airframe and the Merlin engine was not merely good, it was transformative. The high-altitude performance exceeded any other fighter of the day. The aircraft could now operate at 40,000 feet, where the Allison version had been helpless. Speed at altitude jumped to over 430 miles per hour. But there remained a massive logistical problem. Rolls-Royce was already manufacturing Merlins at maximum capacity for British aircraft. They could not produce enough engines to satisfy both British requirements and the enormous American demand that would follow once the United States Army Air Forces recognized what they had. The solution came from across the Atlantic. The Packard Motor Car Company in Detroit, Michigan, had obtained a license to manufacture the Merlin in the United States. This is where the story takes another crucial turn. Manufacturing a Rolls-Royce Merlin was not like manufacturing a conventional American engine. The Merlin had been designed by craftsmen for craftsmen. Many components required hand fitting by skilled workers. Tolerances varied between individual examples. This was acceptable when you were producing hundreds of engines per month with highly trained technicians. It was completely unacceptable when you needed to produce thousands per month with workers recruited from automobile factories. Packard's engineers faced a fundamental challenge. They had to Americanize the Merlin without degrading its performance. This meant re-engineering the manufacturing process from the ground up. They redesigned casting processes to achieve greater consistency. They standardized tolerances across thousands of components so that parts from one engine would fit perfectly into another engine. They introduced statistical process control, measuring and tracking variations to catch problems before they cascaded into failures. They developed dedicated tooling that ensured consistent quality regardless of which worker operated the machinery. The techniques that Packard developed during this wartime project became foundational to modern aerospace manufacturing. When you fly in a Boeing or Airbus today, you are benefiting from principles that were first proven in the desperate effort to produce enough Merlins to win the air war over Europe. Packard designated their version the V1650 series. The V1653, based on the advanced Merlin 63 with improved high-altitude performance, became the engine that transformed the P-51B Mustang into the war-winning escort fighter. At its peak, the Packard plant in Detroit was producing over 3,000 engines per week, double Rolls-Royce's entire British output. The most produced variant was the V1657, which powered the iconic P-51D with its distinctive bubble canopy. At 1,315 horsepower at sea level, it could pull the Mustang to 437 miles per hour and sustain combat operations at 40,000 feet. Are you following this engineering investigation closely? Hit the like button if you appreciate understanding the technical details that changed history. And consider subscribing for more deep dives into military technology. But range remained a critical limitation. Even with its Merlin engine, the Mustang could not escort bombers all the way to targets deep inside Germany and back. General Henry Arnold, commander of the United States Army Air Forces,
read the after-action reports from the August 1943 raid on Schweinfurt and Regensburg with growing horror. 60 B-17 flying fortresses had been shot down. Nearly 600 airmen had been killed or captured in a single day. The bombing campaign could not sustain that level of loss. The solution involved multiple engineering modifications working in concert. Additional fuel tanks were incorporated into the airframe. Disposable drop tanks, which could be slung under each wing, extended range dramatically. The British had actually pioneered the concept of external drop tanks for the Mustang, another contribution that is often overlooked in histories of the aircraft.
With these modifications, the P-51 Mustang could now fly not only to Berlin and back, but as far as Warsaw. There was no enemy aircraft plant that remained out of range. The strategic implications were immediate and devastating for the German war machine. The Luftwaffe could no longer count on distance to protect its factories, its airfields, or its supply lines. A North American Aviation Internal Memorandum dated August 25, 1943, 1 week after the Schweinfurt-Regensburg disaster, documented the urgency. The Army was requesting fuselage self-sealing fuel tanks in as many P-51 airplanes as possible. The urgency was based principally upon the losses that the Allies had experienced. This was no longer a matter of engineering elegance. It was a matter of survival. By 1943, the new Mustangs with Merlin engines began pouring into the European theater in massive numbers. The United States Army Air Corps had initially been skeptical of the aircraft. They had their own fighters, the P-40, the P-38 Lightning, the P-47 Thunderbolt. But the performance numbers from the Merlin-equipped Mustang were undeniable. They immediately ordered 2,200 P-51B aircraft. The aircraft changed the fate of the war. Its dual role was to defend B-17 and B-24 bombers from enemy fighters while simultaneously destroying the Luftwaffe. With wing tanks drained and jettisoned and fuselage fuel consumed, a flight of Mustangs could engage in sustained combat operations over targets deep in enemy territory. There is a profound lesson in the forensic analysis of the P-51 Mustang's development. The original aircraft was not a failure in the conventional sense. It was a victim of mismatched components. The airframe represented the cutting edge of aerodynamic design. The wing was revolutionary. The cooling system was innovative. But none of that mattered because the engine could not perform at the altitudes where combat occurred. It was a chain of causation that almost led to strategic defeat. The weak link was identified not by Americans, but by British engineers with hard-won combat experience. The solution came not from corporate competition, but from international collaboration. The Mustang that entered service in 1942 with the Royal Air Force was a British-specified, British-named, British-requested aircraft built by American manufacturers. The name Mustang itself came from the British. The drop tanks were designed to British specifications. The bubble canopy that became iconic on later variants was another British innovation incorporated into the design. The transformation from a low-altitude disappointment to a high-altitude champion required the Merlin engine, developed by Rolls-Royce in Britain and then manufactured at industrial scale by Packard in America. It required the recognition of the problem by British test pilots and engineers who understood what combat demanded. It required the willingness of American manufacturers to learn from foreign designs rather than insisting on domestic solutions. Edgar Schmood, the lead designer at North American Aviation, was himself a German immigrant who had trained across Europe before coming to America. The aircraft he created was not purely American any more than it was purely British. It was a transatlantic synthesis,
an engineering collaboration that transcended national boundaries at a moment when national boundaries were being contested with fire and steel. The physics of the problem were clear. Atmospheric density decreases exponentially with altitude. An engine that produces adequate power at sea level will lose power as it climbs unless it has some mechanism to compensate. The Allison's single-stage supercharger was inadequate for this task. The Merlin's two-stage system, with its intercooler to manage the thermodynamic consequences of sequential compression, solved the problem. This is not a matter of opinion or national pride. It is a matter of physics. The manufacturing challenge was equally clear. Rolls-Royce had designed an engine for skilled craftsmen. Packard had to redesign the manufacturing process for mass production without degrading the performance that made the engine valuable. The solution involved statistical quality control, precision casting, standardized tolerances, and dedicated tooling. These techniques were not mysterious. They were the application of systematic engineering to a problem that had previously been solved through artisanal skill. The strategic implications were transformative. Before the Merlin Mustang, American daylight bombing raids over Germany suffered unsustainable losses. After the Merlin Mustang, the Luftwaffe was systematically destroyed. The correlation is not coincidental. The aircraft provided the capability that strategic bombing required to succeed.
The P-51 Mustang earned its reputation as perhaps the finest fighter aircraft of World War II. But its secret, the reason it could dominate the skies over Europe, was not just the airframe or the pilots. It was a British engine designed by British engineers, identified as the solution by British test pilots, and then manufactured at American scale by Packard engineers who figured out how to build it by the thousands without sacrificing the quality that made it work. The chain of causation is clear when you examine the evidence forensically. British need led to American production. British specifications shaped American design. British combat experience identified the critical flaw. British engineering provided the solution. American industrial capacity scaled that solution to the dimensions required by global war. This is not a story of American genius or British genius in isolation. It is a story of systematic problem-solving across national boundaries. It is a story of engineers who recognized a weak link in a chain of causation and fixed it before that weak link led to strategic disaster. The P-51 Mustang, with its Allison engine, was a competent, low-altitude fighter. The P-51 Mustang, with its Packard-built Merlin engine, was a war-winning weapon system. The difference was not the airframe. The difference was the heart that beat within it. Every engineering system has a critical path. Every chain of causation has a weak link. The skill lies in identifying that weak link before it fails catastrophically. In the case of the P-51 Mustang, the weak link was identified in time. The fix was implemented rapidly. The result was an aircraft that could escort bombers to Berlin and back, engaging enemy fighters on equal terms at 40,000 feet. The result was the systematic destruction of the Luftwaffe and the achievement of air superiority over Europe. The lessons of this engineering investigation extend far beyond aviation history. Complex systems fail at their weakest point. International collaboration can solve problems that no single nation can solve alone. Manufacturing at scale requires different engineering than manufacturing for artisans. And sometimes, the solution to your most pressing problem is not to design something new, but to recognize that someone else has already designed
what you need.
The British Purchasing Commission came to America in 1940 looking for fighters. They found a company that could build an exceptional airframe. But that airframe needed a British heart to reach its full potential. When the Merlin was mated to the Mustang, the result was not merely a good aircraft. It was the aircraft that saved the daylight bombing campaign. It was the aircraft that destroyed the Luftwaffe. It was the aircraft that helped win the war. If you followed this forensic analysis all the way through, you understand that history is rarely as simple as national myths would have us believe. Subscribe to the channel for more investigations into the engineering secrets that shaped military history. Like this video if you appreciate the technical depth, and share it with anyone who wants to understand how the P-51 Mustang became the legend that it is. The evidence has been examined. The chain of causation has been traced. The weak link has been identified and explained. The P-51 Mustang's secret was never really a secret at all. It was a British engine, built to British specifications, identified by British engineers as the solution to an American problem. And when American industrial capacity combined with British engineering innovation, the result changed the course of the war. That is not mythology. That is forensic fact.